I welcome you all to Nazarbayev University. It certainly is a privilege to be a part of this Digital Kazakhstan lecture series and give this lecture to you. My topic today will be Introduction to Machine Learning. I am the Department Chair of Robotics. I am not from Computer Science, but you will understand that robotics and computer science are very related to each other, and machine learning is a joint topic which we study together. You can just email me through this email whenever you want to get further information on this lecture, or to discuss other topics for collaboration, or to get further information on machine learning or robotics. And at the same time, you can go to our laboratory website to get more information about our research. All right. So, what is my relation to machine learning? Now you will see my doctoral work. The robotic leg prosthesis. This is an amputee wearing this leg. It's artificial. It understands his intent and generates those motions. It has inside more than 70,000 lines of code. It understands the user intent by processing the sensor signals and stating that I want to walk forward, I want to walk backward, I want to climb up the stairs, I want to climb down the stairs, I want to sit down or stand up. Whenever the supervisory controller switches to one of those modes, then the underlying middle-level controllers generate the motor commands for those motions. So it infers the user's actions.
More pauses for the technical terms.
It infers the user intention based on sensor processing, and it uses supervised learning, which is a machine learning technique. So, this was around 2007 and 2008, approximately 10 years ago. Since 2011, for the last 7 years, I was fortunate to be a founding faculty member of Nazarbayev University. I am really proud of it. I am the Department Chair of Robotics, and at the same time, I am running this ARMS research laboratory. We conduct research with the young people of Kazakhstan, our PhD students, postdocs, MS students, and bachelor students on machine learning, robotics, control theory, and so on and so forth. So, today I might state that I do this or I do that, or I might sometimes say that we do this or we do that. In that case, you should always assume that I do all of this work with these young people. We should just give them the credit as well. So, I conducted some machine learning work at Vanderbilt University in the United States. Now, do we conduct any work here in Kazakhstan? Yes, we do. We are extending those intent recognition methods for lower limb prosthesis using new sensor types. This is one of our latest papers. By the way, here I just need to stop and give a small anecdote. When we were publishing our first papers in Kazakhstan, one of the reviewers stated to one of our papers that it is not possible to do this. I don't believe that the researchers have conducted this experiment really. Afterwards, we started making videos for all of our research projects. And we hated that reviewer, but the video we did in response to his work won the IEEE Best Multimedia Award that year. So, as philosopher Nietzsche states, something which does not kill you certainly makes you stronger or better. So, let's have a look at this work. Here, you are seeing one of our teaching assistants who conducts research in our laboratory. She is wearing a depth camera. This is different than the regular cameras what you have in your phones. Your cameras are showing the intensity of red, green, and blue channels. This camera, on the other hand, shows the distance of each pixel in that viewpoint. So it gives us a 3D representation. Do you see? Whatever is close is green, whatever is further away is red. This is something great for robotics, and we wanted to use this for the first time for intent recognition. Instead of processing the sensor signals inside the prosthesis, we wanted to make the prosthesis look to the outside world and understand what is around it. And in order to do that, as a machine learning project, we firstly started with database generation. We collected data from healthy subjects, 7 males and 5 females, such that we have a balanced data set. Afterwards, our researchers annotated this data, and for each frame of image, depth image they got, they assigned one of these 5 class labels: standing, walking, running, stair ascent, and stair descent. And afterwards, we just did a machine learning analysis in which we pre-processed this data, we extracted features, we reduced these features, then we passed it through some type of machine learner, specifically the support vector machines, and deployed this algorithm on an embedded system. And we published our results. This is one of the results. We will study this further. This is called a confusion matrix. And here is the real world of experiment. The subject walks, and then the prosthesis states that I am going stairs down. Now I am walking. It does that by processing the data which you see on the lower left side. Right now the person is walking. The person will stop and start standing right now. And the prosthesis mode changes to standing. It does that in real time by pre-processing this data. There are millions of instructions running at every second in order to do this. Now she will decide to run, and the prosthesis will, the system supervisory controller will understand that she wants to do running. So it's short walking and running. So luckily, we are the first research group in the world who can do intent recognition using perception sensors rather than the internal sensors of the prosthesis. In a way, this is similar to autonomous driving research for the autonomous cars. Now, in the remainder of this talk, you will understand the subcomponents which makes this happen. Now, most probably some of you are thinking that, is there a typo over there? There is an equal sign and question mark at the same time. But I am actually asking a question to the audience. Is artificial intelligence the same as machine learning? Yes or no? No, it is not. Artificial intelligence and machine learning are two buzzwords which are used interchangeably. However, artificial intelligence is a broader concept, which is basically what we call the machines being able to carry out tasks in a way that we would consider intelligent. According to the more formal definition of tool, intelligent agents are any device that perceives its environment, takes actions that maximize its chance of successfully achieving its goals. For instance, your Roomba ground floor cleaning robot is an artificial intelligent device, even though most of the things which are written in its code are hard-coded, and it's a reactive system. It goes, hits the wall, it understands that through its sensors, and changes its direction. To you, it looks somewhat intelligent. Yes, it is indeed as intelligent as a cockroach is for navigating around your room. But we have much smarter systems. What do the machine learning systems do? What is the main difference? Here, I give you the real answer. The machine learning is a subfield of artificial intelligence. Machine learning deals with data. That is the ability to learn using data without being explicitly programming what to do. And right now, this is becoming much more popular, and its size inside this bigger artificial intelligence field is growing and growing, because nowadays we can generate much more data than before. What is one of the primary reasons? One of the primary reasons are these devices. Everybody wants to have smartphones and then generate as much data as possible, and willingly, without thinking about their privacy, upload it to the net. Another one is that we have right now enormous amount of storage. The cost of storage is very low. And also our bandwidths are huge. We can upload data at 100 megabits per second to anywhere we want. So theoretically, a person through periscope can see my daily life with 1 second of delay anywhere in the world if I want it through my cell phone. And that just gives us lots of opportunities to generate data. But what is an example of a machine learning problem? For instance, you just want to detect your spam emails, and you collect data from users who click which emails are spam. This is called labeling, and we do it. When we just do that labeling, we are telling that one mail is spam or not. We can take that information, process through different algorithms, and at the end generate some type of machine learner which will be able to automatically tell whether a message is spam or not. That way, we have a machine learner, an algorithm which learns through the data and without being hard programmed can do a specific task for us. Now, in my lectures or courses, I always like to give the historical context. Let's look to the beginnings of artificial intelligence. It is very hard to pinpoint the starting time of any field in science and technology. If we will do this for the artificial intelligence, we can just mark this seminal event, Dartmouth Summer Research Project on Artificial Intelligence. Around 10 researchers, the forefathers of artificial intelligence, came together in 1956 in Dartmouth in the United States, and they discussed topics including computers, natural language processing, neural networks, theory of computation, abstraction, creativity, cyber-physical systems, and so on and so forth. So these people include John McCarthy, who is the inventor of the Lisp programming language and introduced the concept of garbage collection for programming languages. He also invented situational calculus. We just kind of have Marvin Minsky, who figured out the concept of perceptrons and paved the way for the artificial neural networks and today's deep learning algorithms. We just have Arthur Samuel. He just did the first computer programs which play games, specifically in this case the game of checkers. And he also invented the text writing system, and so on and so forth. Here we have the Claude Shannon, who invented information theory, and thanks to him we can do compression of our data and also do lots of other things in telecommunications. Now, of course, you might think that these are very smart people and whatever predictions they will do will be correct. Let's see what Marvin Minsky said in early 1960s. Within a generation, I assume 10 years is a generation, the problem of creating artificial intelligence will be substantially solved. 1960, let's say one generation, 10 years. Let's give some additional room, 1975. We are in year 2018 and we are nowhere near that solution. Herbert Simon also stated that by 1985, machines will be capable of doing any work that a man can do. I can guarantee you, you can visit my robotics laboratory, the robots cannot do 99% of the works we do. They can do some things, and they are very good at that, but many other things we do, like walking in an unstructured environment, is extremely hard for robots. Let's look to the DARPA Robotics Challenge, in which teams from the best universities and research centers around the world competed to understand the state of robotics, which uses machine learning and artificial intelligence extensively. Where is it? So the robot is trying to understand the surrounding environment and trying to walk. It falls. It tries to open the door. It falls. It tries to walk on an uneven surface. It falls again. This one, another fall. It tries to go through the door, try to understand what the door is, and it falls. Here, the robots are not working in factories. They are working in unstructured environments in which they need to perceive their environment and understand what it is using artificial intelligence and machine learning. Again. don't think that these are researchers who are not good and that's why the robots are not working. These are the best Korean, German, American research teams with millions of dollars of research funding. Therefore, we can confidently state that machines cannot do the things we do yet as good as we do. Indeed, they are very far away from that. Now, of course, maybe the simple things we think that they are easy and simple are not so simple, and hard things are not so hard. Let's look at this. IBM Deep Blue in 1997. It won against Garry Kasparov, the best chess player of humankind, and it won. And I should just confess, it was not even machine learning, it was artificial intelligence. It was a machine which was sorting and searching through some high number of different scenarios. Then, that was a structured game. The choices are high, but not so high. But we have this problem of natural language processing. In 2011, IBM Watson won in the game of Jeopardy. You just have pre-structured natural language questions to the audience, and they try to answer, and Watson won the $1 million prize against the best human players. What happened recently? One of the last bastions of the humankind was the game Go. It has a very large search space, and large search spaces are scary for the machine learning algorithms. But using deep learning, which mimics the human brain, the AlphaGo software started winning against the best human players as well in 2017. So in these games, in structured environments, where we can define what the game is clearly, using lots of data or simulation, the computers are winning against us. Now, what is the reason of those successes? Even though Marvin Minsky and Herbert Simon's predictions about the future of machine learning were not correct, another prediction turned out to be extremely robust. It is Moore's law. It's from the Intel Corporation, to the best of my recollection, the chief executive officer. He stated that the number of transistors in a dense integrated circuit will double approximately every 2 years. And he told in his initial statement, I expect this to happen for the next 10 years. And afterwards, it became the best example of a self-fulfilling prophecy in the technical world. Every 10 years, the experts state that Moore's law will end. Every 10 years, it survives. How? The transistor count is increasing all the time, but the individual technologies are coming to a plateau. Here, for instance, a single thread performance maxed out. The CPU frequency maxed out. The maximum amount of power we can process through these CPUs maxed out. But what is the new trick which we are using? We are using the parallelism. We are using on the same chip multiple small CPUs. We call them cores. And thanks to that, it is surviving. If you want to make some predictions about the future of the Moore's law, I recommend you to read International Technology Roadmap for Semiconductors. It's a report written every 2 years by the sector leaders of semiconductor industry. Now, the topic of our talk today is not semiconductor industry, it is machine learning. And it is an introduction talk. And if you want to learn it further, this is the knowledge base that you need to have. It is mathematics and computer science. You need to know calculus, linear algebra, discrete mathematics, probability and statistics, and optimization theory. linear and nonlinear optimization. Then on the computer science side, you need to just master a couple of programming languages, whichever you want. C, C++, Java, Python, MATLAB, or R. You need to know the data structures. You need to know algorithms, databases, networking, computer architectures, and parallel programming. If you get a master's degree in data science or computer science, you will learn these type of subjects. Now, let's look what type of machine learning that exists. So, if we are talking about learning, then we are talking about between a teacher and student relationship, isn't it? And the different types of machine learning can be categorized by those teacher-student relations. So, we have the supervised learning, in which the teacher is the human fully. We have augmented supervised learning, in which the teacher is the human and machine, a human which uses a machine to do the teaching task. Teaching in this case is assigning labels to the data in our data set. For instance, what does augmented supervised learning mean? When I am doing an object recognition task, I need to assign a label to every single object in an image. So in augmented supervised learning, the algorithm uses image segmentation and creates bounding boxes around the object itself. Then the human expert goes and clicks to the correct type of object for those bounding boxes. That way, that image segmentation done by the computer helps to the person, human being, for data annotation. But human is involved. Then we have semi-supervised learning, reinforcement learning, and unsupervised learning. These are, as of now, research problems, and we don't have very many deployed products which use those methods. However, the supervised learning and augmented supervised learning is current state of the art, which is being used in very many different products and services. Main focus of our talk today will be this part, the supervised learning part, in which we just have labeled samples of input-output relationships. So, what does a supervised learner do? Supervised learning is the machine learning task of learning a function that maps an input to an output based on input-output pairs. It infers a function from labeled training data consisting a set of training samples. Each sample is a pair of an input, typically a feature vector, to an desired output state value. Supervised learning is also called as pattern recognition and classification, and is a mature technology. People are doing supervised learning since even 30s. The Fisher discriminant analysis was introduced in 1932. But of course, the more modern algorithms were introduced after 1960s. Most of the machine learning systems which are deployed in the real world are supervised learners. Now, let's look at the machine learning process. At the very beginning, you define your problem. I want to diagnose breast cancer from the breast mammogram data. Firstly, you gather lots of data. Afterwards, you look at that data and try to understand what type of features are providing the information. Then you do data cleaning. Some of the data might have noise. You might filter it, or you might discard those samples. And afterwards, you start the real machine learning process, the model building. You extract features, you reduce the dimensions. Depending on the type of the problem, you either do classification or regression. At the end, you need to benchmark and present your results. And if the results are good, you need to deploy it as a product or service. Now, everybody who thinks that they are doing machine learning, the starters, they think that they will spend most of their time doing the classification, using some software, or writing their software for that. In reality, 80%, and that's a conservative estimate, in my opinion, 95% of the time is used for preparing your data, collecting the data, understanding your data, and cleaning that data such that it is suitable for machine learning purposes. So, one might ask, why do we need to learn? I am very smart and I can write a program which will solve any type of problem. So, for instance, if you want to write a payroll software for the accounting department, you don't have to use machine learning. You can just write the software by yourself, hard-coded. However, for some tests, such as separating spam emails from regular emails, there is no algorithm you can use, or that algorithm which you need to hard code is extremely hard to find. Then you need machine learning. Learning is used and indeed needed for these cases. Human expertise doesn't exist. I want to have some type of a robot to navigate on Mars. The better strategy for me to use is the reinforcement learning strategy, because right now I don't know how to hard code that, because we have never been to Mars and we don't have enough information. For instance, I have a task which we are doing regularly, but we don't know how we are doing. For instance, every 2-year-old baby can speak. Nonetheless, if I ask the best programming expert in the world to write a program which to understand, recognize the speech, and generate speech, they will fail. So for that, we just need machine learning. Or we just have some certain situations which are constantly changing, so there is no fixed ground truth. For instance, if you are trying to optimize the network routing, you need to just kind of gather the data in real time, process it, and output a new solution based on that data. There is no general solution. Similarly, for predicting the oil prices or doing some type of financial interactions in the stock exchange, this is the case. Or the solution needs to be adapted to every single case. For instance, I want to do biometric analysis. This I can do if and only if I provide the data to the. Now, what is the essence of learning? The essence of learning is data is cheap and abundant, even though still expensive to process, but knowledge is certainly much more expensive and scarce. In the learning, we want to create a good and useful approximation to this data. And we are data-centric because we are generating enormous amount of data at all times, and human beings are willing to share it with the service-providing companies, which I find very interesting. You just had last week a talk on big data and data mining, so I can skip this slide. But the definition of data mining is this. Machine learning methods applied to large databases is called data mining, and it has lots of different application areas. From now on, our talk will start to become a little bit more technical. I will glance over the technical details, but you are more than welcome to email me, and we can schedule an appointment and discuss about them in great detail afterwards. So I told that in supervised learning there are two different approaches depending on the output type of the data. One of them is classification, the other one is regression. The classification problem is predicting discrete class labels outputs for a sample. For instance, here I have two axes, which is my input data, income versus savings. I have some high-risk people and low-risk people. If a person has a low income and low savings, he is a high-risk person to issue credit. I just generate a rule and a boundary which divides the output into two different categories, which are discrete, which are low risk and high risk. On the other hand, I want to fit some curve on top of my data, and it's called regression. I am provided a set of points, these red stars here, and on top of them, I need to fit a curve which will describe the behavior of those points as close as possible. So at each instant of the domain X, we just have a continuous value predicted. This is the regression problem. For instance, if I try to predict values outside of my variable range, I call it extrapolation. If I try to predict a value in between two data points, I call it interpolation. If I want to predict the future of a time series, that is called time series prediction. For instance, I want to predict the future value of the oil in 1 month, 2 months, or 3 months. The biggest problem you will face when you are trying to do machine learning is overfitting your data. Let us understand the concept of underfitting and overfitting. Let's have a look at this data for the uppercase. Here, I see my data points. My objective is to fit some type of line which will go through this point. If I underfit that data, I just use a line model which has very few parameters. It is not rich enough, and I fit this red line. It certainly does not model the underlying phenomenon closely. What I should do is to fit the red line. That I did do here with a third order polynomial. However, there is this risk. I want to fit all of my data points perfectly. That is called overfitting. Every single point is perfectly fit. However, what you see is that even though my underlying phenomenon is this a green line, here I have big spikes. That is because I overfit. What I do in this case is actually trying to model the noise and uncertainty in the data as well. And that should be prevented. We have methods for doing this. The same case is here. This is a classification problem. The purpose of my supervised learner, the classifier, is to find a line or boundary which separates the red axis from the blue circles. And my algorithm, we don't know what algorithm that is, finds this line. But certainly this is not a good line, because I know that I could have just kind of have a line similar to this, and it would just kind of generalize my data much better. However, in the case of overfitting, my learner just kind of like finds this surface which correctly classifies these points, but that is more than what I should do, because most probably these two axes are the human labeling annotator annotating the data incorrectly, or my measurement device is making some type of erroneous measurements. How to prevent this? In order to prevent that, we are using a statistical method called cross-validation. In the cross-validation, we are using a resampling scheme for training. In this resampling scheme, we divide, for the k-fold cross-validation, which is the most commonly used version of it, we divide our data randomly into 5 folds. In each of these folds, we have 1/5 of the data allocated for testing and 4/5 of the data allocated for model training. Using the training data in each fold, I create separate models. For instance, model 1 is trained using these folds, using these parts, and it is tested on that. At the end of this process, I estimate my test error for new samples by taking the average of each of these models on the individual testing data. This prevents overfitting. And by doing this over 5 different folds, we are just kind of decreasing our error margin for the test cases. This is a must-do for preventing overfitting. There are different types of cross-validation. K-fold cross-validation is very popular. Another one which is very popular is leave one out cross-validation. Now, I just told that at the end, I just report my average result. What is my average result? Now we will just kind of look at that. Usually, we report our accuracies. Accuracy is number of correctly classified samples over total number of samples. For instance, For the paper for which you have seen the video at the beginning of this lecture, we provided these two tables. Classification accuracy for different combinations of learning algorithms and dimension reduction methods. So we have here 94%, 94.1% accuracy. That means that in my testing data set, my algorithm could classify 94% of the samples correctly. That might be a good or bad result depending on your problem and domain. If I want to understand whether that single value is good for my problem or not, I look at a further indicator. That's called the confusion matrix. Confusion matrix has two axes. One of them is the actual class of the testing data. The other axis is the predicted class of the data. So, if my actual class and predicted class are the same, in other words, my data is on the diagonal, that is good. I classify my samples using my machine learner correctly. If I am off the diagonal, then I have a problem. For instance, in this case, we are classifying walking as running, running as walking, and standing as walking. At that instant, I go back to my data, try to understand what is the reason of this problem, and I do some type of cyclical process. Let me go back and show you something. That is exactly this part. When I build my machine learning model, I repeat this process until either I run out of my money, so I cannot pay the data scientists anymore, or I don't have time. So it is either the Astana Day in the summer or Day of Independence in the winter. Because that is when the project ends in Kazakhstan. So far, we talked about the concept of supervised learning. We talked about overfitting and underfitting this data. We talked about a method to prevent this overfitting, which is called cross-validation. And at the end, I just summarized some very basic methods of reporting the performance of our algorithm. Now, in the remaining part of this talk, before starting the third part actually, we will understand how one of the very famous machine learning algorithms work. This is the nearest neighbor algorithm. It is the simplest to understand. Here I have a point. One of the classes is the class of positive marks. The other one is the class of dashes. So what do you expect this unknown record is? It's of course a plus, isn't it? Because the three nearest neighbors are pluses. So very easy. So now let's look at these cases. You just answered this question, great. What do you think for this neighborhood my class should be? What do you think the case here is? Is it minus or plus? But when I just increase the size of my neighborhood, it becomes minus and plus 50-50. What if I just kind of like tell that you should look at the three nearest neighbors and I have one minus and two pluses? But it is the same data, so you are telling for the same data it is minus and plus. So this is the fundamental weakness of this method. It just kind of is a lazy learner. So what does a nearest neighbor classifier do? What it does mathematically is finding the Voronoi diagrams around this data. It just finds polygonal regions which define the classes around these points. So everything within this for a one nearest neighbor classifier should belong to this class. And in order to do these things, we need to find our nearest neighbors for every new sample. How can I find my nearest neighbor? I need to use some distance metric. For instance, I can ask you, am I closer to Kökçetağ or am I closer to Shymkent right now? You would obviously tell Kökçetağ. And because Kökçetağ is 200 kilometers away from here, So my distance metric would give 200 kilometers versus 1,500 kilometers. The mathematical way of describing this process in data is using metrics. One of the metrics which we use very frequently is called the Euclidean metric. The fundamental problem with the k-nearest neighbor problem is to choose the number of neighbors. So here, if I choose my neighbors as 5, it will be plus. If I choose my neighbors as 20, 30, it will be minus. And you don't know how dense your data is and how many new points you will get. Therefore, this algorithm, being non-parametric and not looking in the densities of the data, is somewhat weak. In addition, this algorithm has some problems with data scaling. As I showed you, you have a distance metric which calculates your distance using multiple dimensions. If those dimensions are not correctly scaled, as in the case of here, the third one, which just ranges from 10,000 to 1 million, will dominate. So, in order to use this algorithm, you need to carefully scale your data. These are all pre-processing steps I need to do before doing machine learning. I sometimes tell to my students, you are like a KNN. Because KNN is called a lazy learner if they don't study. Why is this a lazy learner? Because KNN classifier does not build a model explicitly. Instead, it just kind of takes a new sample and does all the computation it needs to do on the fly. In order to prevent that problem, people have created data structures such as KD trees. So this just kind of shows that the importance of the data structures for machine learning. Otherwise, our algorithm will take a huge time to run. This is the first one. We have seen the strength of it. It's extremely simple and intuitive. We have seen the weakness of a KNN. The number of neighbors are rather arbitrary and it causes problems. Here is another algorithm which is also very frequently used. It is called decision trees. The main strength of this algorithm is that at the end it creates simple rule sets for us which we can interpret as human beings very easily. For instance, we can use this and create 5 sets of rules for a doctor to diagnose a disease. So, what does a decision tree do? So this is a tree structure. For a computer scientist, a tree is not something green in the forest. A tree is this structure in which we just have some branching statements. If x1 is greater than v10, w10, you just kind of go to this side. Otherwise, you go to this side. Here, you branch into 2 classes as well. And if you don't branch further, you have the leaves of the tree. And you are either class 2, class 1, or class 1. So now the problem becomes, how do we generate this tree? Because the learning process is exactly figuring out how the structure of this tree and how these branching conditions are found. Just kind of. The tree which you have seen in the previous slide is a univariate tree. It means that at every branching part, you just do your decision based on a single variable. The resulting space division is with these type of boundaries. Sorry. So I can just kind of divide it into a half space like this, and that half space into this. So I just have the class C2, class C1, and the class C1 here. Each of this is just kind of like found by the half division of the space. So how are we learning these classification trees? We are using a concept invented by Claude Shannon from the information theory called information entropy. And we are trying to maximize our information entropy in this process. I will not enter the details of that, but I want to show you the pseudocode of this algorithm. This pseudocode is similar to a recipe. It tells to a computer scientist how to program this algorithm in any type of programming language. It is mainly done for human understanding. It is independent of a specific hardware or programming language specification. By reading this, I know how the mathematics of the process will be converted to the code, and I use this to implement this algorithm in any software language I want. So we create these trees, and we just kind of like go through the pruning process. We are reducing the complexity of this tree. And in order to do that, we just set aside a pruning set, and we just kind of remove the leaves until our validation set accuracy does not improve anymore. And at the end of this whole process, I have this type of output. For the C 4.5 type decision tree, I get this 5 set of rules. For instance, if the age of the person is greater than 38.5 and the person has been in this job for 2.5 years, then the income level of this person should be 0.8. A person can read this and understand this very easily by following these branches. So this corresponds to what? If the income level is greater than if the age is greater than 38.5, this branch. If the years in job is greater than 2.5, this branch, then I go here. This I can convert using a script to a very easy set of rules, and afterwards I can use this as a decision support system wherever I want. This is one of the main strengths of the decision trees. Now, until the deep learning became the de facto state of the art in machine learning, the previous king was support vector machines. And interestingly, this has been invented by Vladimir Vapnik, who studied in Uzbek State University in 1958. In 1990, he immigrated to the United States, started working in Microsoft, and created this new machine learning technique called support vector machines. And he did something very smart. He stated that why should we solve a harder problem than to solve the actual problem? It's a very nice philosophical trick. He tells that I don't care about my data's density, statistical properties, and so on and so forth. My job is separating the data into two parts. Therefore, I will only look to the part where the data is close to each other, and I will just define some support vectors in order to separate them. This was an extremely smart idea. However, his main strength lied in his mathematical abilities. When you go through the derivation of the support vector machine, you understand the elegance of the method and the genius of this person. So, this is just a mathematical definition of a sample is X, consists of the feature vector X and the class label RT. RT is +1 if the data sample belongs to the class 1. It's -1 if the data belongs to class 2. In support vector machines, what we are doing is this. We are trying to find these points, which we just kind of call support vectors, which separate the class 1 from class 2 by ensuring these equations. W transpose times X transpose plus the constant W0 should be greater than or equal to +1. Then all of my data points are here. If the other case is true, then all of my data points are here. So if I can find the coefficients of this vector and this constant, then my classification problem is done. Let me finish the support vector machines and then we will continue later. Now, when we look at this, what type of problem do you see? The answer should be the real world is nonlinear and this method works only for linear data. And in order to solve this, again, as a strike of genius, they invented the kernel trick. They took the nonlinear data and projected into a feature space in which it can be linearly separated. This is a very powerful trick. Another visualization of that is here. Here, in the input space, you know that this data can be separated from the outside data using a circle. But the equation describing a circle is nonlinear. X squared plus y squared is equal to some constant square. On the other hand, if I just kind of like create some type of radial basis function projection, I can project the data in this axis in which the central values are high and outside values are low. Then this data becomes totally linear. So this is the kernel trick. Normally, when we do machine learning, we tell our students always try to reduce the size of your feature vector. But the kernel trick is a counterexample. However, the way the kernel trick works is that this kernel trick is embedded to the heart of the optimization problem, and we actually don't project the data in reality. We only do it for the dot product of the coefficients. We have polynomials vectors, kernels, radial basis kernels, and so on and so forth. And this makes the support vector machines an extremely powerful classification method. Now, I think that this instance is a good instance to stop because we will start the perceptrons. We will learn the artificial neural networks very briefly. Then we will look into the deep learning, and then we will just kind of like look into the opportunities which machine learning can bring to us. So let's have a break of 15 minutes.
Before you go, guys, first I'll say a couple of brief words. Number one, we warned you that this talk would be technical. It's one of the most technical talks. Number two, we don't expect you to understand all the technical details, of course. There's no examination today. Number three, I'm going to suggest that actually we're doing this talk because you requested it, because machine learning is becoming a very powerful tool. And then the good news for you is you don't have to learn this, but you might have some young people that you would like to learn this. And if you think you have a need for this kind of technique, you have these young guys that you can send for this training, or you can hire some of our young guys that we're training every year. Dozens and dozens of them who go through this, who have all of those mathematical classes, all of those computer science classes, all of this kind of professional exposure with these examples. So remember the purpose of our seminar, to familiarize all of you with these concepts, to explain how they work and where they might be applied. So I'm trying to give you a little bit of relief from this, because in a way it might not be your problem so much as your guys' problems later. So please, I want to thank Dr. Varol for this very good introduction. I ask you to be prompt with your tea break and whatnot to come back so that we can go through the second part, which includes
less technical.
Less technical, more applications. And at the end, we can talk about whether you have problems that might be solvable with this approach. At the conclusion, I'll mention, we're doing something in response to your requests to organize professional training, a master's degree that emphasizes all of these fields that we've been presenting to you. So if you have guys who need this training, in cooperation with Zerde and all of you, we're organizing such a program now. But we'll give you more details later. Thank you. Take the break. You've earned it. Okay, everyone, welcome back. In the interests of time, we're going to start now. I know some of our participants are still drinking their tea. Now, again, good news. The most mathematical part is over. We will summarize some technical elements and look at some big ideas and maybe some applications. I remind you, I challenge you, that if you have good ideas or good projects, either for big data, data mining, or machine learning, we're available for you. And Dr. Varol will, at the end of the talk, make this information known to you, and we can stay afterwards and have some consultation. In the meantime, I want to give him every opportunity to complete the second, actually the third part of his presentation. So please, Dr. Varol.
Right. This part will be less mathematical, and I will skip those parts such that we can finish this talk at 3. However, I will stay here to discuss any type of machine learning project you might envision with you afterwards. So, what is our brain? Our brain is an information processing device which can do speech recognition, vision, reasoning, and learning. And in machine learning, essentially, we want to mimic how a brain works. But this is extremely hard because, firstly, we don't know exactly how a brain works. Secondly, brain is made out of biological cells, but computers are made out of transistors. What type of difference does that introduce? So, our brain consists of 10 to 11, in other words, 100 billion neurons. Our computer chips right now have close to 10 billion transistors. Neurons are much more complex than a single transistor. They can do nonlinear operations. However, brain operates much slower compared to the computers. Your computers can make decisions 4 billion times a second. On the other hand, your brain just kind of works at 40 hertz, 40 times a second. Every neuron is connected to 10,000 other neurons, and memory and computation are at the same place. So now let's look at the components of an information processing system. What are those? Firstly, the computational theory corresponds to the goal of computation and abstract definition of this task. Then we have a representation and algorithm, and at the end we have the hardware implementation of the problem. Let's just kind of like solidify this with a simple example of sorting. The computational theory of sorting is to order a given set of elements. The representation for that might be integers, and the algorithms to that integer sorting might be the bubble sort. And on top of that, the hardware implementation might be compiled executable C code for an Intel processor. Now, why are we doing artificial neural networks, and why don't we do another method to achieve machine intelligence? For instance, this is a bird. The first plans of Leonardo da Vinci to make a flying machine was to replicate a bird. But today, we know that a flying machine, an airplane, does not have to have feathers. And we might have completely different type of methodologies for flying. But for machine learning, until we find a better model than the natural brain model, we don't have a better alternative yet. So we are at this stage, more or less. The bird and Leonardo da Vinci's mimicking the bird's behavior. It was not successful until Wright brothers made the real airplane, which has still wings, but not with feathers. So how did we take this idea of mimicking the brain to the machine learning field? It was the perceptron introduced by the Marvin Minsky. It is basically a model for a neuron. It just does a very simple function, and by itself, it is something very weak. However, if you just connect it in a network, making lots of input feature vectors multiplied by lots of constants and mapped to lots of outputs, it becomes powerful. Indeed, this is a single layer. What we are doing in artificial neural networks is to create multiple layers. The main problem with this approach is the computation. Training multiple layers takes huge amount of computational time, and it also requires huge amount of data. Now, at the beginning of the lecture, I told that now we have the data, and recently we also started having the computation necessary for this process. What am I talking about? Deep learning. Deep learning, in very simple terms, is artificial neural networks on steroids. They use the convolutional neural networks and create a very high number of layers and use lots of data to train this. Right now, it performs much better than any other algorithm for large data sets. We can do things which we have not imagined that we can do 10 years before. The main disadvantages of deep learning is that it takes a very long time to train. So basically, it requires specialized hardware. Those are called GPUs. They are produced by the company NVIDIA. And it requires huge amount of training data. Now, here, this video summarizes very nicely how a GPU works. A CPU is in all of your regular computers, and a CPU is a multi-purpose beast. It is similar to this robot. It can do lots of things, but it can do one task at a time. For instance, here, it will just do something amazing. This robot will do painting by itself. One by one little dot at a time. Now here you see a different device. This device is lots of simple devices bundled together. Each of them can do something very simple, but 3,200 of them together will do something great. Let's have a look. What do you think this will do? It will maybe do a smiling face, but as you can see, 3,200 of these items are connected. It is exactly how a GPU, which does deep learning, works. Let's wait them to click and see what it does. Voila. Mona Lisa, in an instant, without sequential processing, completely parallel processed. Each item did something very simple, but altogether they did something great. So this technology right now allows the deep learning to work. Otherwise, the artificial neural networks, the theory was available since 1960s, and convolutional neural networks since 1980s. So, hopefully, I was able to scare you from machine learning enough. Now, still, if you are interested into the topic and you want to start doing machine learning, I recommend you this software. This is Weka. It is from the Waikato University in New Zealand. Has been downloaded more than 100 million times. I checked it yesterday. And it is an open source graphical user interface based tool for machine learning. So, if I want to apply machine learning, and I am not a specialist, this is a very good way to start. If I am a specialist and I want to do some rapid prototyping, I want to see which algorithm works for my problem better, this is a very good way to start as well. You can download it, and using the tutorials in 2-3 hours, you can do your basic machine learning tasks with this. Of course, Weka does not contain feature extraction routines. You cannot just feed raw images to it and expect it to classify it. However, as a rule of thumb, my boss was always telling that if the data set can fit to an Excel spreadsheet and you can just look at that in an Excel spreadsheet, you can process it with Weka. So it's a good starting point, and you don't have to know any of the underlying math, but still, you might just kind of do some very basic mistakes if you are not a specialist. Now, I have been told that you are vice ministers at the policy making level, and the rest of the talk will be non-technical and looking to that policy level issues. This gentleman is a former CME professor. He is the person who did the first speech recognition system, Kai-Fu Lee. He is the CEO of a venture capitalist company in China. He gave a talk very recently in MIT, to the best of my knowledge, on the state of artificial intelligence in China, and he compares United States and China in that talk in terms of technology, markets, products, capital, and policy. So at the end, he concludes that both of these countries are quite advanced in all of these four aspects. United States has some still advantage in these four. Nonetheless, on the policy side, he points out that China is better. They just have a way to make very fast policies, get them executed, and they don't care about the privacy of the people as much as the people in the United States do. Now, one of the general conclusions which I derived from this talk is this. Countries with bigger population, which can generate more data, and more research spending, which translates into more product and services, have a clear advantage due to the snowball effect. So this is an unfortunate statement because we don't have those advantages in Kazakhstan. Our technology is not yet very advanced. We don't have very many advanced tech companies. Our market is 18 million people. There are lots of young people, so market adoption of any new technology is fast, but still it is small. We don't have yet many products and services. And capital, as I will show in the next slides, is not there. We just don't have much research spending. So it would be a good task to start thinking about how we can progress in this machine learning-based innovation in Kazakhstan. I don't have the answer to this question. Nonetheless, right now, due to Hollywood, maybe, we like to idealize things. For instance, we think that Elon Musk does the electrical cars. Or we just tell that Steve Jobs makes the iPhones. In reality, it is not the case. It is all thanks to a huge ecosystem. This is how a tiny part of California works and creates all of this machine learning ecosystem called Silicon Valley. What do they have? They have the data infrastructure companies which provide the hardware, infrastructure, and services. Then they have companies which specialize on collecting this data and providing it to building block and learning services companies. These people just kind of like create machine learning tools which are used by other companies using the infrastructure provided by Android, Microsoft, Apple operating system, and so on and so forth. Lots of different technologies. At the end, they end up with lots of services and products which everybody more or less right now uses for free. But actually, in reality, you are paying them with your data. They take that data, feed it to the data collection companies again, and this cycle continues. They are creating this positive feedback loop to grow their machine learning ecosystem. If you want to be successful in machine learning in Kazakhstan, at least in a small scale, we must replicate this one way or other. Again, I don't know how and why, how this can be achieved. Now, we are Nazarbayev University. In my opinion, Nazarbayev University has the highest technological readiness level in machine learning in Kazakhstan. And we would like to collaborate with your organizations. We would be delighted to do that. However, task definition, preparation of data, and feasibility study takes lots of time and effort. So, we are open to collaborate with all of you if you can allocate trained personnel equivalent to 12 months of effort. The minimum duration should be 3 months. So, basically, if you can tell that I have 4 great engineers who can prepare the data for you, who can work for you, and we just kind of don't want any results in less than 3 months, that is a good start. Usually, when most of the government agencies or companies come to us, it is 1 month before the day of Astana on July 6th, and they want a new UAV to be built in 1 month such that they can just demonstrate it in that national holiday. That is not a good way to do collaboration. You provide the list of projects. I would like to talk about them in detail afterwards, but specifically right now, I don't know and understand how they are related to machine learning. It is not obvious from their titles. And here comes the other part of it. This is the R&D spending of different countries. And believe me, in machine learning related research, everything is related to R&D spending because the most important ingredient is how many machine learning specialists you have who can just kind of put their intellectual workforce to work for that specific problem. So, USA spends $473 billion. China, 409. Let's go down. Russia, 42. Here on 17th, my home country, Turkey, 15.3. They allocate 1% of their GDP to research and development. Israel, a tiny country, allocates 4.3% of their GDP to research and development. Now we come to the number 57, 58, and 59. Kazakhstan allocates 0.17% of their GDP to research and development. So it is great that we are here together talking about machine learning, but with this amount of research funding, it is, even if it would be fully allocated to research and development, that would, in machine learning, that would not be enough. Now, you might state that these are countries, maybe they are conducting research in other fields, they are not conducting this research in machine learning, and you might claim that machine learning research might be cheap. So, we have here the companies which spend the most amount of money to research and development. Let's look whether these are machine learning and data companies or not. Amazon.com. It is retails, but all of its research is on machine learning, robotics, and related fields. It spends $16 billion per year. To the best of my knowledge, the national budget of our Kazakhstan is $32 to $33 billion for 2017. So they are just allocating half of it to research and development. Second one is Alphabet, a solely data company. It is basically Google. They spent $14 billion. Where do they spend this money? They don't make big buildings or so. They have big buildings, but they spend it to bring the best and brightest minds in the whole world to their company to work for themselves and create these algorithms. Underneath, Intel Corporation, the chips, the infrastructure part. Then Samsung, all of your phones and related technologies, how to gather the data. Then here we have Volkswagen, but Volkswagen just kind of spends lots of money on autonomous driving. Then we have the Microsoft Corporation, a software company. Here we have two pharmaceuticals, and you might think that, okay, at least we found something which does not spend the money on data. No, they spend their money on personalized medicine, basically analyzing your genes such that they can create special drugs for you. That's where they spend their money on. And at the end, we just have Apple, another data and software-based company, all of them spending over $10 billion of research funding on these topics. So, now, where to start? For instance, if I would be a government official, I would tell that let's do some machine learning and robotics related research, and let's do something very flashy which the public can see, because that would be a great public relations success. And I would just kind of open the technical magazine, and in the first page, most probably the news will be about the Amazon Prime Air. It is Amazon's, the company which has the highest amount of research and development spending in the world, flagship project. It is their main PR project as well. I bet they don't spend less than $1 billion on this project alone. Now, you might just kind of think that making a demo is equal to the introduction to of a product or service, but it's not. I showed you at the beginning of this lecture a prosthesis, a robotic prosthesis, and it was working quite well. It has been licensed by a prosthetics company, and since 10 years, they are working on that with a team over 10 researchers to get it into the market. At the end, they will introduce it. This year, I guess they did, and they will sell it for $90,000 per item. Nonetheless, they have put in it huge amount of research and development spending. Now, I personally never give up, and I always try to find a place where we can just make a contribution where we have an advantage. For instance, we should just kind of think about these type of things. Kazakhstan is the leading producer of uranium in the world. So use machine learning for intelligent automation in mining and processing of uranium to maximize added value. Because most probably there will be very few number of other companies who would be interested in doing that, because they are just not the market leaders in production of this item. Kazakhstan is emerging as a logistic corridor between China and Europe. They are just making these roads. I see it whenever I go to Shymkent. And really, the traffic is increasing. So if you can use machine learning and operations research to optimize the routes and minimize the delays of cargo transported, that would create some amount of added value as well. In addition, whenever I open the news, there is just kind of like a corruption in customs news. So use machine learning to mine the customs data to flag the suspicious cases, such that you just kind of need to handle the cases before they happen. Or left bank of Astana is ultra modern and it is built nearly from scratch. Maybe it might be a good idea to make Astana the first open air machine learning laboratory in the world. Another country which is trying to do this is Singapore. They have a small city, it's their state, and they are just trying to convert it into an open-air machine learning laboratory where they gather all the data. Now, if you liked machine learning very much, and if you would like to learn more about that, this is a very nice textbook on machine learning. We are studying it in the 4th year of our undergraduate curriculum, Introduction to Machine Learning by Ethem Alpaydan. I recommend you to read it. Secondly, if you want to have a bird's eye view on where this field is progressing, please read this new Royal Society of United Kingdom report on machine learning, the power and promise of computers that learn by example. Now, if you want to read how machine learning and artificial intelligence will affect the future of jobs, read this report of McKinsey Global Institute, Jobs Lost, Jobs Gained, Workplace Force Transitions in a Time of Automation. And in addition, Germany is introducing the Industry 4.0 paradigm in automation right now. Please go and read their personal report on smart manufacturing for the future, which might give you hints on how these things will transform. This is not deeply related to our topic, but if you want to just kind of like read some of my favorite books on economic development, one of them is on how Asia works. It just basically summarizes the successful economies of Asia, which are export-based, and how they succeeded. And another one is by a Chinese economist, Justin Yifulin, The Quest for Prosperity, which basically states that if a country is not highly developed, they should not invest in the most advanced technologies. They should just kind of invest in technologies which they can reach and make useful products where they are competitive in 5 to 10 years. And that's that book. So with this note, I am finished with my lecture slides. If you have any questions, I would be more than happy to discuss.
Very complete, very comprehensive, and I think for those that are interested, you have a path forward. On the one hand, I'm a little discouraged by one thing that Dr. Varol has said. We don't have the ecosystem here to be super successful in all areas in terms of the application of these technologies to the national economy. How can we hope to succeed against players with much better resources and much greater investment? But he also answered this question. We can be a little bit selective. We can choose projects that have an impact. We can go after projects that maybe are less interesting for others and more relevant for our circumstances. And I think this is a good approach. We should be selective. We should understand what these technologies can do, in which ways we can apply them, and which projects have a good connection. Now, he made a good offer. I'm not sure if everyone understood it. He offered to you the ability to collaborate with his team, which, as I mentioned, is maybe not just the best in the country, but in fact quite competitive in the world. And he suggested if you have an area where you think you could have some achievements, you have some good challenges, and you're willing to commit some resources. He gave the equivalent of 12 labor months, 12 person months of effort, maybe 4 engineers, and some time, not 1 month, but a quarter, 3-4 months at least, time to acquire the data, to organize the data, to apply some of these algorithms, to refine and run through the process and maybe get some answers. So I offer this, he has offered.
Yes.
I extend the challenge and suggest that if you have such circumstances and such people and such problems, that we talk about them. Because there are some achievements that could be accomplished in the coming 3, 4, 6, 8, 12 months that might be of interest and utility to you to move forward some of these very ambitious digital Kazakhstan objectives. At the beginning of the talk, I made the same offer related to big data and data mining. You may have such projects. We have people. One thing that we've done in these last 7 years is to build very specific capacity at the instructions of the government based on global best practices, American models in particular, to try to train the next generation of, let's say, knowledge economy workers. And this is where we are. We're demonstrating now why the Deputy Prime Minister has established the Center of Competencies here, why we're working in collaboration with Zerde to reach out and help support all of the groups that have been charged with tasks to implement as part of this initiative. There are things we can do in 3 to 6 months. There are things we can do in 12 to 18 months, and so on. The new chair of our Department of Computer Science reminded us earlier that we're generating, based on your requests, a new graduate program. If you give us some of your young engineers, we can work with them over the next 2 years and create specialists who know these things. So we're working with you to help achieve these goals. In addition, there has been some discussion about maybe some micro-training courses, professional development in specific targeted areas as early as this summer, in areas such as data mining, bioinformatics, and potentially here in this topic of machine learning. Now, I'll pause. We'll formally close the session. Those of you who have questions for Dr. Varol, please stay. Please stay and we can continue our discussions. Thank you very much.
Thank you.